we're going to be looking at a classic Japanese circle geometry problem here. What they're doing here is they give you three different circles. These three circles are all tangent to one another, and we want to find a connection between their radii. So radius x, y, and z, we want to find a connection between them. So to do this here, first consider drawing a line going out this way, exactly parallel to our line here. Notice this meets at 90 degrees then. I know that the length from here to here will also be z, which means if the entire length from here to here must be x, because that's the radius of this green circle, therefore this length here must be x minus z. Likewise, the length from here to here, because this is a radius of the blue circle, is also z. So therefore we have the length of the hypotenuse of this triangle, right? The length of the hypotenuse of this triangle would be x plus z. So now I know that the length of the hypotenuse is x plus z. I know the length of the leg is x minus z. I don't know what the a value is here. What this leg is, I'm going to label that with an a. Okay, let's do the same sort of trick on the other side. Again, if I draw a horizontal line going out and drop that down here, once again we have our right angle. Once again, this length will be z. So the length of this hypotenuse of the triangle is y plus z. The length of this line segment here, I know the entire length is going to be y, and this length under here is z. So then y minus z will be this length. This is our b value. Again, I don't know what that is. So we can put this information together because these are right angled triangles. So if I look at the small triangle I've created here, I have Pythagorean theorem, in which case we get a squared plus x minus z squared is x plus z squared. Likewise, for the larger triangle, we have b squared plus y minus z squared equals y plus z squared. Okay, I want to create one other triangle. And the triangle I want to create, I want to connect a plus b together. So to do that, we have to start fresh. Okay, so now I want to incorporate a plus b. So what I'm going to do here is I'm going to draw a horizontal line going across, draw a line going up, and I'm going to create this triangle right here. Okay, well, what is the measurements of these lengths here? First of all, this is my a plus b. Right, this line segment right here, this is my a plus b. As we saw in the previous diagram, each one was defined as a and b. The sum is your a plus b. Okay, so now I want to find the length from here to here. What do I know? Well, I know the length from here right to the bottom, right? That length is going to be y, which means the length from here to here will also be y. But I know the length from here to here, since if you take a look here, I know this length here represents my radius. This too represents the radius. Those are the same lengths, so I know this is x. So if the entire length here is y, this length here must be y minus x. Now what's the length of the hypotenuse here? Well, your length of the hypotenuse here would be the sum of both radii of the circle, in which case there that would be x plus y. So now we have another equation we can create. I know that a plus b quantity squared plus y minus x quantity squared, i.e. the sum of this leg of the triangle and the sum of this leg of the triangle, must equal x plus y quantity squared. Okay, let's put all these together and see what we have. Okay, so now we have all three equations kind of written down together here. Again, I want to find a connection between the radii of these circles. So let's take a look at equation 1. I want to expand this out and see what I can do with it. So I have a squared plus x squared minus 2xz plus z squared equals x squared plus 2xz plus z squared. Okay, well, does anything happen here with this one? Well, yeah, look what happens here. The x squareds cancel, the z squareds cancel, and I end up proving that a squared is equal to 4xz. Okay, let's take a look at equation 2. Well, using equation 2, I have b squared plus y squared minus 2yz plus z squared equals y squared plus 2yz plus z squared. And going through this one here, the y squareds cancel, the z squareds cancel, and end up showing that b squared, in this case, is 4yz. Okay, let's take a look at equation 3. What does that give us? I'm going to leave the a plus b as it is. And if I expand out this expression here, you get y squared minus 2yx plus x squared is y squared plus 2yx plus x squared. And yet again, the y squareds cancel, the x squareds cancel, and this time I get a plus b quantity squared is 4yx. Okay, let's see what we can do with these three relationships we have. So now I want to write these in terms of a, b, and a plus b. So a is going to equal 2 to the root of xy. Taking the square root of both sides, likewise b is going to equal 2 to the root of yz. And lastly, the sum here, in this case a plus b, is going to be equal to 2 to the root of xy. So now what does that mean here? Well, that means that when I sum the two a and b values, I get 2 to the root of yx, but that has to equal 2 to the root of yz plus 2 to the root of xz. So now we have our relationship. A plus b has to equal 2 to the root of yz plus 2 to the root of xz. This is not how it's typically written, and we can clean it up a little bit, make it look a lot nicer. So we're going to divide across by 2 to the root of xyz, 2 to the root of xyz, and 2 to the root of xyz. When we do this here, you'll see you get cancellation. Obviously, the 2's all cancel. You also notice here, the only thing I'm left with here is 1 over the root of z is going to equal 1 over the root of x plus 1 over the root of y. So now we have a direct relationship between the radii of those three circles. 1 over the root of z is equal to 1 over the root of x plus 1 over the root of y. So this is a classic Japanese geometry problem here. I thought I'd show it to you guys here. Check it out, study it, and definitely comes up a lot in math competition questions. Thank you.